So I have a significantly easier job than Lisa, because she has to talk about real things that are really happening right now. And I get to just talk to you about the future, which is ever-changing and contains all possibilities. I'm only going to be talking about ground-based detectors, and yeah, it kind of works. So over here, so this is supposed to be gravitational wave frequency on this axis, and then some different science targets up here, and some different detector technologies down here. I'm over here at the high frequency end and ground-based detectors, and I guess we'll move down in frequency and off into space shortly. And then to relate this to the past, you saw this in Lisa's talk. So Lisa talked to you about things up to about here, and I'm going to start there and go off into the future. All right, so that's the context of this talk. So the question that I spend my time thinking about is how can we do better than what we're currently doing with our detectors? So we have Advanced LIGO, we have some Advanced LIGO design. Lisa showed you how we're struggling to achieve that design sensitivity, but we can also think about how do we go beyond that design? How do we do better than that? The obvious answers are that you can start by just doing what we did to go from initial LIGO to Advanced LIGO, just do more of the same, right? So try to go even higher power, heavier masses, better mirror coatings, better materials, whatever. So that's this kind of obvious thing. Just use the same hammer again. The other thing you can try to do is use new technologies. So squeezed light counts as one of the things that's new. It turns out that it's been successful enough, thanks to people like Lisa who spend all their time working on it, it's been successful enough that has become now, let's say, standard technology or conventional technology. It's actually very tricky stuff. So squeezed light is a new thing for us. We can imagine moving to other wavelengths. We can try to operate cryogenically. There are lots of ways that you can try to use new technology to improve your detectors. That's sort of everything you can do in the context of the current facilities. So on the bottom half here, I have the things that you can think about if you're willing to build an entirely new facility. And the first and most obvious thing, I'll say this, but probably everybody knows this, the gravitational wave signal scales with the length of your detector. It's a strain. So if I make it twice as long, my signal is twice as big. So the most obvious thing to do for any gravitational wave detector, if you want to make it better, is just make it bigger, right? You can't do that in the current facilities, obviously, so you have to go somewhere else and build a longer detector. That's the first, most obvious thing. Another thing you could do is go underground, and that can reduce the low frequency noise that your detector has to deal with. And another thing you can do is say, I'm going to try some completely new concept for detection. The ones I listed here are not completely new because I have trouble with things that are really way, way out there. But you could at least do things like imagine changing the shape of your detector so that you use a triangle instead of an L. This lets you measure gravitational wave polarization. You could imagine overlapping multiple detectors that operate in different frequency bands. We call this a xylophone. There are all kinds of interesting ideas for new things you could do, still in the context of interferometric gravitational wave detection, but new stuff. I'll start with the top half of this. So the future of LIGO, and I specify LIGO here as opposed to Virgo or other detectors because this is our particular plan for LIGO. Other detectors have similar sorts of plans. The immediate future, just after the stuff that Lisa has been talking about and where the little arrow started on my second slide, is an upgrade that we call A+. And there's a similar upgrade planned for Virgo. The idea here is that we improve on the squeezing that we're going to be using in the current detectors to move to something we call frequency-dependent squeezing. This lets us reduce the radiation pressure noise as well as the shot noise. And the second part of this is ongoing research in coatings looks promising. So we're hoping to replace the test masses we have with new mirrors that have better coatings, and that will reduce the thermal noise in our detectors. These two things are what we can do in the really near term. And here we're talking early to mid 2020s. And this is a proposal that's actually in the works, going in to get money now. So it's that level of sort of immediate future. Farther down the road, we have a concept that we refer to as Voyager. And the Voyager concept is really trying to express the idea of what's the best we can possibly do in the current facility. So keep the vacuum tubes as they are, but you can do anything else you like. Change the laser wavelength, cryogenics, whatever. So this has to do with R&D that's in progress right now in labs that are investigating new technologies that we can put in the current detector facilities. So the first two of these, in terms of the sensitivity and to some degree the science that we hope to get out, is expressed here. So this is the usual sensitivity plot. Probably all of you have seen these things. Certainly you have, because Lisa just showed them. Audio band detection, strain on this axis, down is better. So here's where we are right now in blue. This is the Advanced LIGO design, which we hope to approach in the next sensitivity run and achieve in 04, the next observing run rather. And then the A+ design is more or less just a step down by a factor of 2 by improving these two noise sources. So improving the, again, quantum noise, that's pretty much all of this, and thermal noise, which is this part over here. Frequency-dependent squeezing is what gets us this piece by reducing the quantum radiation pressure noise. In terms of the science we get out, this should correspond to roughly 7 times greater rate for binary neutron stars and 4 times higher rate for binary black holes relative to Advanced LIGO design. So it's not, it's not a huge gap in terms of sensitivity, but remember our event rate goes with the cube of this sensitivity. So that's the little balls over here supposed to show, is that we start with a small ball in the middle. If you increase the radius of the ball by a factor of 2, which is essentially increasing your sensitivity by 2, you get a factor of 8 in terms of the volume. So that's why we get excited about these relatively small changes. The details of the Voyager concept are starting to develop now. So we have some pretty good idea of what sort of technologies we would like to put in if we got to do anything we wanted to in the current facilities. And this will be sometime late 2020s is the rough time scale. I should say that a lot of this is being worked on by Rana Adhikari at Caltech, and he'll give detailed timelines for this that pushes out to 2028 or something like that. So we have some idea what the time scale would be. But it's really a major upgrade based on using new technology. And the things that we're looking at right now are silicon optics and slightly longer wavelength lasers, so either 1550 nanometers or 2 microns. That allows us to use new coating materials which have lower thermal noise. And so this could get us another factor of 2 beyond beyond A+. One of the interesting sort of science targets of this is it means that the distance to which we could detect binary black hole systems starts to become cosmologically interesting. We get out beyond a Z of a couple, out to a Z of roughly 5 as the maximum distance for binary black hole systems. So there starts to be some kind of new science targets where you get out of the local universe for this type of detector. Okay, so then my favorite topic is actually farther down the road. You could think of this as job security. I make sure that I have something to do for a long time. And so the R&D that I've been talking about is stuff that we hope to put in the current facility, but of course we're looking farther down the road and trying to develop technologies which will also be useful in a new facility. But those things get us kind of factors of 2 in improvement. If we want to take a really big step forward, so another factor of 10 in sensitivity beyond, say, Advanced LIGO, we're going to need to build something new. So going beyond LIGO and Virgo, I could also put Cogra and everybody else in there, but going beyond the current facilities means probably going to places like this, someplace really big and really flat, or going underground. And there are 2 main concepts right now which are being developed for next generation detectors. We call it third generation detectors. So the one that's best developed at this point is a European concept called the Einstein Telescope. And this is the classic figure they have for the Einstein Telescope. And what it shows is an underground facility which is triangular in shape, nominally 10 kilometers on a side and operating 6 interferometers on top of each other. So this is a xylophone type configuration like I had mentioned previously. This work is under development right now. There's actually a lot of development happening on ET and all of the various design choices made in the conceptual design are being reconsidered to see what's really the best way to get science per dollar. So this effort is something which is very serious happening right now, and things like site selection are happening, looking at how much it's really going to cost to bore tunnels of a certain size and everything else. So the ET development is getting into the details and really looking to maximize the science in the context of what we know right now about the sources. The second concept that's out there, and this one's my baby, so I'll take the credit here, but also the blame, is a concept called Cosmic Explorer. This idea is somewhat simpler than ET. The idea is really just to take a LIGO type detector and scale it up by roughly a factor of 10. So it's above ground, L-shaped detector, 40 kilometers on a side, single interferometer. Right? Like I said, relatively simple. Of course, when you get into the details of how you do this, it's not quite so simple. But it goes for the brute force approach of just make it bigger, as much as you can. I should say that this is also under development right now, and we're hoping to get funding to bring this to the same level of the ET design study, which they are now developing to the next step, looking at costing. So both of these 3G concepts, or next generation concepts, are currently under a lot of development. In fact, there's a global effort to develop the science case for third generation detectors. This is by GWIC, the Gravitational-Wave International Committee. So there's a lot of work going on right now thinking about the future of this field. So these are the two concepts we're considering. To give you a rough timeline for this, we're over here in the Advanced LIGO, Advanced Virgo, soon to be CAGRA phase. The hope is that in the early 2020s, early to mid, we'll be operating A+. And as we get into the late 2020s, we'll be operating something like the Voyager concept. So best we can in the current facilities. While we're doing this, of course, we're doing R&D on new facilities. This is like ET and Cosmic Explorer. Then sometime in the early to mid 2030s, like I said, ET is a bit ahead of Cosmic Explorer, so it might happen sooner. But sometime in the 2030s, we hope to be building and operating these new facilities. Okay, so I haven't been showing a lot of sensitivity curves as I talk about these concepts, so I want to quantify here briefly what I'm talking about. Up here in gray is the current sensitivity for the LIGO detectors, and you're seeing the design curve, which is here in blue. So A+ is this first step down to do better than the Advanced LIGO design. That one's shown in red. As we move to Voyager, you go to this green curve, and I should say that for every one of these curves, you'll see slightly different versions available out in the literature. And the reason is that we have a choice of how the high frequency detector sensitivity evolves, and we're always trading between having an increased range, so a higher volume for detecting sources, and the desire to have high frequency information to look at mergers of, merger events of anything, but in particular by neutron stars right now are driving the high frequency part of the sensitivity. So this choice pushes us in both directions. It depends on what is hottest at the moment as to how you choose your sensitivity curve at high frequency. So there's some variability you'll see in these things, but mostly the general progress is from blue to green. We're really just improving technology, so things are just getting better technology here. And then moving from green to orange is essentially saying, if I keep this technology and put it in a 10 times longer facility, this is what I get. I include the Einstein Telescope curve here, but again, it's under a lot of development right now, so probably that's going to change. I would not want to exclude ET. The idea, though, is that ET will be underground, and so we'll have access to these lower frequencies that a surface facility would not. So we'll see how the ET sensitivity curve evolves relative to the others. The general idea is, as we move to third generation, we're able to take this next big step, which gets us farther out in the universe in terms of our sources. So this plot quantifies that in terms of the distance to which we could detect systems. So the compact binaries would fall along this axis, and I've picked as a metric the total source frame mass of the system. And I'm assuming circular binaries, no spin, the simplest possible thing, just so I have a simple case to plot here. And on this axis is the redshift at which we could detect these sources. The solid curves, so this is the solid curve for Cosmic Explorer, is the absolute maximum distance. Right? So to say that technically it would be at that distance you detect 0% of your sources. Right? If you go beyond that and realize nothing, that's really the edge. If you say, what's the distance at which I detect 10% of my sources, that's this curve here. Right? So this shaded region is where you're getting from, I'm detecting 10%, I'm detecting nothing out there. Right? And the next step in here is 50%. And then the same thing is given for ET, for the curves I had previously. for Voyager here, and for Advanced LIGO design here. Right? So you can see that the distances we can get to with these third generation detectors are out here at redshifts that are of 10s, 30, 40, 50, almost out to 100. And that's far enough out that probably you don't, well, at least some of you wouldn't expect to find anything out there. Others of you might be hopeful for primordial black holes to be found out here. And what that means is for signals like the ones we've been detecting so far, you'll have very high signal-to-noise ratios, something around 1,000, for something like GW150914. So very high SNR signals from things which are at a redshift of a few. And the bioneutron star systems sit over here, so a total mass of about 3. And the distance at which those, so the maximum distance at which we could detect these is something like a redshift of 10. Again, you don't expect much of a population out there, but what that means is that you get to sample the entire population before your detector runs out of sensitivity. Right? So you expect probably most of the population of these to be at a redshift of a few, 2 or 3. And that's in here where we're seeing a good fraction of the population. Something to keep in mind is that gravitational-wave science in the era of third-generation detectors will be significantly different from what we're used to right now. We've just recently entered an era in which we have, oh my goodness, we have 1 event, right? That's the kind of level we're at. Oh, we have 2, right? And it's very few, and we have to be happy with what we get, and we only get the things which are really close. Right? So I'd like to say that the current instruments, while they're very impressive and very sensitive, they're also the least sensitive device you can have to actually detect something. Right? There's a lot of room for improvement. So if you try to count the number of sources you would expect to have in a third generation network, what you find is that you're talking about hundreds of thousands of sources, events per year, right? Hundreds of thousands. And most of these will be just where the picostar formation is, Z of a few. Right? And that's what I mean is it's not determined really so much by the detector sensitivity, that'll determine the quality of the signals, but the number of events is no longer limited by your detector sensitivity. You're basically seeing all of them, or at least you have a good chance at all of the compact object mergers which happen. People often ask about the stochastic background that will result, or foreground, from these sources. I think that for binary black hole systems, they're likely to be separable. So even if you take every binary black hole merger in the entire universe, it's still 1 every 10 or 15 minutes. And they don't last that long in our band, so that's fine. But for the bioneutron star systems, it might be a challenge to separate them, because they stay in band much longer, and there could be many of them. So if you start thinking about the science you're going to do with these things, you have to think somewhat differently. You should imagine that you have very high numbers of sources. And it means that if you're thinking of maybe just doing population-based studies, you might not need good sky localization for that. You care about just what's the mean and median values for various population statistics, of which you'll have, again, very good statistics, so those will be meaningful. If you want to do precision tests, you won't be in the situation you're in right now where you have 1 or 2 events and you try to use them all in the most optimal way because you're really starving for signal-to-noise ratio. Probably you can focus on the best few events, and those will be the ones which really determine the outcome for a test where you're trying to do something that's precise. So you use the nearby events where the signal-noise ratio is very high. And then we shouldn't forget that there's probably a lot of physics to be done with the things you don't see very often. So either signals from core collapse supernova, or if you have a highly eccentric merger, then you can really explore some really interesting physics there with these highly eccentric mergers. And those probably don't happen very often, but with a detector like this, you should be able to pick them up. And then any number of other exciting things that I'm not sufficiently knowledgeable to speak about, but things like cosmic spring cusps and whatnot like that, maybe we'll be detecting those as well. Let me focus for a moment on the high SNR events. So this plot was intended just to show the signal-to-noise ratio for a binary black hole merger, 30 solar masses, circular, the usual sort of boring system that we now see all the time. That's kind of a crazy thing, right? That we now think of these things as just boring. But anyway, as a function of redshift. So at a redshift 10, for a system like that, if it's optimally oriented, you expect to come in at an SNR of about 100. Right? And as you go closer, redshift is something like 1, you have an SNR of several hundred. And if you get to something which is like the events we're seeing now, or the closest of them, that's redshift sort of 0.1, that's how you get to an SR, something like 1,000. Okay. So for this, you would expect to be able to measure the merger phase very well. Maybe you're seeing quasi-normal modes. You might see gravitational wave memory effect. Lots of things you could imagine doing with these close signals. I stole this plot from Salvatore Vitale. And what he has shown here is for GW150914, for our first event, this is the distribution of chirp masses, so the detected mass of the system. And the true value is here at this red line. So it's a statistical, the usual Bayesian posterior type plot that Salvo likes. And if you take this same event and put it in something like Cosmic Explorer, you find that the width of this thing is actually that little red thing there. So that goes from 30.402 to 30.416. Right? So you get very, very good measures of parameters with third generation detectors. The other thing that's important as we move to the future is that right now everyone working on third generation detectors is trying to figure out how we can optimize the science we get out of these. And to do that, we've all come to the rather obvious, but anyhow, conclusion that the more we work together, the better off we are, and the more we plan for the future together, the better off we are. So for third generation, we really need to make all of our science case discussions in terms of the network that we'll have of third generation detectors, not really just the single detectors. So it's easier to understand just my favorite detector. But if you really want to know what the science is you're going to get out, you have to think of the global context of those detectors. So this plot is showing the same sort of range plot, and I'm putting it at a 1% cut. So that's where you'd expect to have, well, 1% of 100,000 means only 1,000 sources. All right, so something like 1,000 sources out of this distance, well, out to that distance. And here you're seeing, the redshift that you can get to, again, with a network is really incredible. You get to very high redshifts. And this is for, let's say if I have one Einstein Telescope and two Cosmic Explorers, it'd be this blue one ET plus a Cosmic Explorer plus a Voyager detector left over from the previous generation, you get the orange one, and so on. Right? So this is the kind of study we're doing right now, is looking at what we get out of networks of detectors. Maybe we're mixing different detector technologies, and then trying to quantify the science we get out and what are the really important metrics for the science we can do with third generation networks. All right, so the message. The message is that in the near term, we will be reducing the noise in the detectors beyond design by roughly a factor of 2. So I'm thinking of A plus here. And near term means early, mid-2020s. As you go farther out using the current facilities, we could end up with another factor of 2, and this would be something like Voyager. Start to get out of the local universe with that. As you go to the next generation, and we're building a network of third generation detectors, we really hope to be sampling the entire universe in terms of the population of compact objects, and picking up interesting new things that we haven't seen before. So I conclude these future detector talks always in the same way. This is really very, very much just the beginning, and you should expect the way that we approach gravitational wave science to change over the course of the next couple of decades. As we go from this relatively small number of statistics, we have to be happy with the few events we get kind of situation, to one in which we have many, many events. And if we want to cherry pick, we can do that. If we want to do statistics, we'll have lots of big numbers to deal with there. So that's it. Thank you.
So, what does this increase of signal to noise do for spin measurements of the known black holes?
Yeah, so it turns out that the spin measurements are right now quite poor. And so first I should say, everything I know about this I've learned from Salvatore Vitale, because I don't usually do data analysis, but I'll do my best to channel Salvo here for you. What he would say is that in the third generation, since we won't be looking at only the closest events, and we're instead sampling the population, the most likely source will be one that you see edge on. Right? As opposed to right now, the most likely source is either face on or face off. And in an edge-on source, you get much better measurements of spin because you can see the precession of the source. So we expect our spin measurements to improve significantly as we go to third-generation detectors.
Erwin?
I'm just curious, how does the noise suppression go with depth of underground placement? And how does the cost go with depth of underground placement?
Yeah, right. So I'll do my best to answer the first one. The second one is much more challenging. The noise suppression as you go down really comes from two things. So the not fundamental piece is that you have less seismic noise as you go underground, assuming you don't create it yourself. So one of the problems going underground is you tend to put fans and things like that. So if you avoid making a lot of your own noise, you get a quieter environment just to start with. And that means your isolation systems have less noise to deal with. So that's the first piece. But the really fundamental piece is what we call Newtonian noise. And this comes from seismic waves, which are moving principally on the surface. And if you imagine a seismic wave passing through the floor, it's some density perturbation which is moving there. And if you subtract off the background, that looks like a moving mass moving around on the floor. A moving mass near our detectors has a gravitational force, just Newtonian gravity on it, and it disturbs our detectors. So this Newtonian noise is something that is reduced as you go underground. There you get away from the surface waves, which are the main density perturbations. You then have to deal with the body waves, so there's still waves that pass through, but they're somewhat less. The other thing that's interesting is that you get Newtonian noise from the atmosphere. So the atmospheric density is much lower, but the pressure changes are much larger in the atmosphere. And so there's a Newtonian noise which comes just from atmospheric changes. And that's pretty hard to shield yourself from. You can make microphones that try to measure it and like this, but it's hard. So going underground gets you away from atmospheric Newtonian noise. Those are the two sort of real fundamental things that you gain by going underground. Of course, the cost is higher if you're tunneling. Apparently that's less true in Europe than it is in the US. The Europeans are better at making tunnels than we are. Carsten here is looking at me like maybe that's not true, but this is what I've been told. So anyway, it's likely to cost more if you go underground. If you're making something which is tens of kilometers long, you're going to do some digging no matter what. So I would say that the cost of the facility as a function of underground or above ground is highly dependent on exactly where on the Earth you plan on building it. I'm looking for large dry lake beds for a 40-kilometer detector. It turns out you can find some of those in the US and elsewhere on the planet that are big enough that you could hope to not do much digging, and then maybe that's the place to build it. But the cost is a much harder thing. So you have to pick a very particular location and evaluate that location specifically.
Can you talk a bit about the prospects for detecting very high frequency signals, say the kilohertz signals from neutron star mergers and beyond? Many years ago, people talked about, I think they're called signal recycling techniques that will allow you to dynamically adjust the band to actually catch that final part of the signal at high signal to noise ratio. Is that still being discussed?
Yeah, I'll respond to this in two parts. So the first part is that as we move from one detector technology to the next, right, our high frequency sensitivity is improving, and the cutoff, as you go beyond 40 kilometers in length, you start to bring the end of it's just the round trip time in the detector starts to be comparable to the frequency you want to measure. So 40 kilometers for Cosmic Explorer is really chosen because that means you can detect signals out to about 4 kilohertz, 4 or 5 kilohertz, and then you start to really lose sensitivity. So that's why you don't go to 100 kilometers, something like that. But up to that point, you're really still winning at high frequency as you improve the technology of the detector one way or another. So that's the one aspect. So just to be very clear, we fully intend for these detectors to be sensitive out to a few kilohertz. And that'll be true as we go on into the future. So just driven by the science, it looks like we have to do that. In terms of signal extraction and signal recycling and all of that, in anticipation of this question, I put this plot in my talk. And this is taken from a note that was by Jamie and Lisa here. And what this is intended to show is a detuned interferometer configuration. It has this sort of classic double dip. And this is one in which you set up the detuning of the interferometer so as to very specifically dig the deepest hole you can out here to kilohertz. All right, so that's sort of the idea of detuning. And what you'll see is that does not get you much beyond a detector in which you just have squeezing. I wouldn't make that trade, right? Technically speaking, this is also very challenging to do, and probably you're not going to be able to do that dynamically, so you would have to decide, for the year of 2035, I'm going to operate like this, right? Are you ever going to do that? I don't think you will, right? So this, to me, looks like a much more profitable and much more profitable, easier, and therefore much more likely configuration.
We will have a discussion about LISA later on, and LIGO we heard already. There is this wall of seismic noise that separates the two frequency bands. And I was wondering if it at all makes sense to think about going to space or the moon or a place where seismic noise doesn't exist and bridging this gap in the future. Did you think about that?
Yeah, so of course Karsten will talk about going to space with LISA. That gets you a frequency band which is somewhat lower, and that people like to notice that there's a gap between the two, which is what I think you're pointing at. There have been detector designs which target that. I think that, I have to be careful how I say this. I'm on tape. The most realistic of them is probably the Japanese Desaigo design, which still will require significant technical development to be realistic. It's a hard band to target because doing it in space is tough. You need to have resonant arm cavities like ground-based detectors in space, right? That's very challenging. Doing it on the ground is extremely challenging because of the Newtonian noise, which goes up by orders of magnitude as you move below 1 hertz. So even though you might get some shielding or some cancellation, it becomes very challenging to access that band on the ground. So the band which takes you from 1 millihertz to 1 hertz is a relatively tough one. The LISA detector is designed explicitly to hit a sweet spot below that, where you can go very, very long with a space-based detector that's not resonant. It's a hard band to hit. So there are people are thinking about it. Like I said, I think Desaigo is probably, at this point, the most realistic design I've seen.
Okay, let's thank Matt again.